Okay, are we live?
Yes. Hello, everyone. Welcome to Temporal.haus, a climate refugee proposal for LA, presented by European Cultural Center, ECC, in Venice, Italy. My name is Rachele De Stefano. I'm head of architecture at the European Cultural Center and the main organizer of the architecture biennial exhibition Time Space Existence. Every 2 years, we invite an international group of architects, designer, artists, academic institutions, and creative professionals working across disciplines to investigate the fundamental topics of time, space, and existence. These are the principles of our long-term research in architecture and the title of our biennial in Venice. With this project, our goal is to create in Venice a platform for dialogue and for research. In the context of this year edition of La Biennale di Venezia, curated by Ashim Sarkis with the title How We Will Live Together, the 5th edition of our exhibition Time Space Existence presents the work of over 200 participants from more than 50 countries, showcased in our venues Palazzo Bembo, Palazzo Mora, and the Giardini della Marina Ressa. The exhibits range from conceptual works, models, videos, site-specific installations, sculptures, photographs. All participants ask themselves what they can do to improve the quality of our life sustainably, with climate change, migration, water, rapid urbanization being the major challenges. Andrew Michler is one of the participants of this year's edition of Time Space Existence, and his project, Temporal.haus, is currently exhibited at Palazzo Mora's 2nd floor. I'm delighted today to have the opportunity to host on our platform a roundtable organized by Andrew about implementing low zero carbon resilient building design. Today, we have with us Andrew, of course, from Hyperlocal Workshop, Jay Hart, an embodied carbon expert from the University of Colorado, Jessica Grove-Smith, who is co-director of the Passive House Institute, Stefan Siemers, director of research and development at Beck LignoLoc, Bjorn Kjerulf, CEO of Ecococon. And thank you all for being with us here today at this panel. I give now the floor to you, Andrew, to start the presentations.
Unmute. There we go. There's my unmute button. Hi, everybody, and a big thank you for the European Cultural Center for putting this Biennale together and helping us kind of connect from around the world with all the different ideas and concepts and processes that we're working with architecture, especially with kind of the environmental approach that you guys are emphasizing this year particularly is very encouraging. And also the program with lots of interaction amongst the participants has been really fantastic to see. So thank you also for hosting this talk as well. And we'll be giving a few presentations, and then we'll have a good 15 to 20 minutes at the end of the program to do a question and answer. So if you're on YouTube, feel free to put a question in the chat, and we'll see if we can get to it at the end of the program. These are some of the most interesting people that I know, certainly in the environmental building world through the years I've been working in it. So it's a great honor to have all of the other participants as well. Yes, my name is Andrew Michler, and I'm based in Colorado. And this is where I live. I live out in the country, but I'm also extremely interested in cities and been going to cities for the past decade of researching. I wrote a book called Hyperlocalization of Architecture, exploring different different work around the world, specifically to kind of the cultural environmental impact of contemporary architecture. And around my house is a giant burn scar, and so I'm always thinking about kind of the changing environment we have. We had a 200,000 acre fire burn right up to our property last year. So it's something that's quite personal to me, climate change and the built environment colliding with the changing climate and conditions, natural conditions. This is the project. Here's the installation that we have in Venice. And you can see the Ecococon panel and the LignoLoc table, CLT table here, and then a display on concept of projects. And certainly that how will we live together was very much on the principle of what I was thinking about as this project was coming into being, the concept. And part of that is the framework for that is it's a good place to start is this ProPublica article that came out, I think last year, titled Where Will Everyone Go? And it was basically examination of how climate change is impacting Central America, especially around agriculture, and how it's forcing large populations both into the city and up north. And I'll read this quick quote from it. By 2070, the kind of extremely hot zones like the Sierra that now cover less than 1% of the Earth's land surface could cover nearly a fifth of the land, potentially placing 1 of every 3 people alive outside the climate niche where humans have thrived for thousands of years. So that's the reality that we're living in. And how will we live together? Where are we going to live, and what are we going to live in is kind of what I'm looking for. So in my proposal, I'm looking at a building that will be housing for climate refugees from Central America, essentially, in Los Angeles. And I chose a place called Wilshire Boulevard. Wilshire Boulevard, in some ways, ironically, is the center of, or the invention of what we call strip malls in the United States. So it was the first place where you went to park and walked to the shop and then went back to your car and drove to the next shop. So it's the invention of kind of the modern America. But it's becoming extremely urbanized, happily. The project itself is near Koreatown, and it's on a kind of a lot. The idea was to take a lot that is quite dilapidated, mostly parking, kind of a very simple single-story building in a dense area. The metro station just came in there, so it's a good place to start thinking about where we can put a larger scale housing, especially in Los Angeles, where the housing pressure is enormous. Part of the concept, or a large part of the concept, was reinventing the idea of the shop house principle. And many immigrants came to the United States and different nations and lived in buildings where they live in the upper stories in the back, and the front would be where they actually did their business, often revolving around food and sharing kind of their cultural contribution in the form of food. So that was the place to start, thinking about how we will live together, how people will be integrated into different places. The other component was I developed a food truck with a friend. It's actually a coffee truck, coffee bar, espresso bar, we call it. And part of it was the idea of how do we release ourselves from the food in the brick and mortar. So we decided to look at food trucks and converted a 1979 Toyota camper, essentially, into a full service espresso bar. And that's been quite successful. It's won architecture awards. It's been a lot of fun to put together. So the idea was how to integrate the food truck culture back into Wilshire Boulevard and bring people back into that enormous sidewalk, that enormous tarmac, how to reactivate that for people again. And then also as a place for, there'll be a commissary kitchen there. There's another place for people who live there to actually be able to work with the trucks, or start their own small food businesses on site. So it's the integration of those different layers and textures culturally is the idea. It's the food pavilion itself, I'm calling it, is quite generous in size, can hold maybe 5-6 trucks. It has a large shaded area for people to queue and to eat their food and to kind of cool down, enjoy an afternoon. The building itself is actually not oriented particularly well, where this is a passive house. And Jessica will talk more about passive house later on, and kind of the principles and ideas around, especially the energy side of it. But our biggest issue was with the lot, most buildings faced west or east. So with a west-facing building, how do we keep it from overheating, for instance? So it's extremely aggressively shaded for where all the apartments are facing towards the west. But at the same time, the apartments have full access to the exterior. It's very simple. It's a building 7 stories tall, mixed use. The first floors is where we have a commissary kitchen, a small bar, public bathrooms like that. Second floor is kind of an open program, and then layers of different types from single people to small families to potentially even larger families, is the idea. And the front of the building is a series of patios that are shared commonly. So people have access from the outside on each floor. And each floor also has an open space, open kitchen. This is something that I hope to see much more often in residential buildings, is more public spaces, so that there's a much more connectivity through the program itself for people, and also creates opportunity for them to invite friends and use the space more actively over time, rather than being stuck in a small box all the time. And lots of other kind of attributes that are really helpful for these scale buildings, especially for these single loaded buildings. We can better naturally ventilate them, creating access to the roof for potentially an open school, and then the shared patio. And the fire escape itself also doubles as a way to egress through the building without necessarily using the elevator and connecting those floors more organically. On the material side, and what we'll talk mostly about today, is the building itself. Now, this is a passive house, so it's a what we call fabric first process. So we look at the energy efficiency of the building, which means the kind of the thermal boundary conditions, and optimize them to reduce heat gains and losses in the building very carefully. We're also using something called an Ecococon straw panel, which is developed in Europe by Bjorn Kirov, and he'll get into some detail on those things. And I was really inspired by his process of developing a 5-story concept using these straw panels. Essentially, they're a certified passive house component, so they're within our energy model already. So he graciously helped develop a 4-story upper part for where all the apartments are. And it's sitting on a podium that's developed in part by LignoLoc, utilizing LignoLoc wood nails by Beck. And they also have been developing a cross laminated timber CLT with a diagonal bracing for a shear. So it makes an excellent podium. So when we put all these components together, we're looking at basically a biomass building that has at least the potential to be carbon sequestering, if not carbon neutral in its fabric, but also using the passive house methodologies. I'll go into a little bit about that later. We're looking at essentially a zero energy or an on-site renewable building as well. So the carbon is very much key to this, because climate change, climate refugees, why put them in buildings that are climate catastrophes, which is essentially what most of modern building is at this point. Ecococon panels, Bjorn will get into specifics, but the first question everybody asks is, well, it's straw, it's going to burn. So this is from Ecococon. The straw of Ecococon panels is compressed at a density of 6.9 pounds per cubic foot, leaving no space for oxygen that would fuel the fire. Straw has a high content of silica, natural fire retardant, which is amazing. When burning, both materials create a charcoal insulation layer on the surface that protects them from flames. So, these buildings are extremely safe. They're extremely durable. The idea of Temporal.haus is how a building can change program on a daily basis, but maybe be a 200, 300-year building that can be deconstructed over time. The wooden nails are absolutely fascinating, and they really help reduce the amount of inputs you have to do to create CLT, so they make it much more available for smaller producers to develop. I'm thinking the potential of having a glue-free CLT out there in the wild would be fantastic. We can also make nail laminated timbers, which are great for long spans like floors, which we're proposing for this building, essentially taking a 6x6, in America, a 2x6 rather, and nailing them together. That becomes a floor slab. So they also can be easily deconstructed. We don't have any steel in the buildings or minimal amount of steel. So you can cut them and deconstruct them quite easily and reuse them. Part of the passive house side is, of course, ventilation. So we are able to use a American company called Ventacity, which developed an HRV, ERV, heat recovery ventilation system. In this case, we're using one on each floor, and we can also use them to distribute the cooling for each apartment. So we can double up with the fresh air system as well as the way of tempering the spaces. There's more technical information on the website, Temporal.haus. We really don't need heating. We need basically a pretty low load for cooling because we're quite aggressive with the window shading, and mostly it's internal heat gains we're mostly concerned about. Even our hot water heaters, heat pumps, add a cooling load to the building by taking the ambient air and heating water with it. So at the end of the day, our operational energy is essentially a negative. It's 130 kilowatts per square meter annual negative, or in other words, we produce that much energy on site, more than we consume in net. So that's quite interesting to find that result, that we can do that with these extremely small loads, especially for conditioning, air conditioning, and low or zero heat. On the materials embodied carbon, I've run a calculation of the project. We're looking at 224 kilograms of carbon per square meter for the building, and hopefully Jay can unpack that number and what this means in the real world. Most buildings are quite a bit more. And I'll have a couple slides. I'll go into what the calculator is. For the PV system, I just wanted to make a quick note, is we had to put a lot of PV on the building to make this building work as a passive house premium, at least potentially a passive house premium building. Passive House Institute helped with the calculations. What we're looking at is two separate systems, essentially, what the graph shows. So in the summer, our peak solar is going to be coming, of course, from a horizontal system on the roof. But on that wall that's facing due south in the winter, it's also going to produce quite a bit of electricity, almost as much as the larger array, this horizontal. And why that's important is because in winter is when our peak heat or peak loads are typically going to be, often with lighting, other things like that, and shorter exposure to the sun. So we want to look at solar production, not on an annual basis necessarily, but on kind of that daily operational basis for it to be a truly net zero energy or an energy positive building. For the Passive House verification and help with the Passive House Institute and quite a bit of tweaking, I was able to see if we can just slide it right into what we call the Passive House Premium. And that's based on the Primary Energy Renewable component of Passive House, which connects the energy consumed with the energy that's produced on site through renewables. One little funny thing is that I found out that when I put in double pane windows to see if and save money, it's Los Angeles, right? All of a sudden my heating load went up quite a bit. So by putting in double pane windows, my heating load was negligible, which means that my distribution system is much more simplified, as well as my energy load. And also triple pane windows are fantastic because they make a much quieter apartment. And you can imagine if you have a busy commercial space underneath with people outside, you can close the windows upstairs on Wilshire Boulevard and be very, very quiet inside the building. So, and it's certainly not very much more expensive, if at all, now between double and triple pane windows. So interesting little fact to see when you're designing these high performance buildings. On the carbon side, this is a quick run through a carbon calculator that we use. Is now available, called the pH ribbon, and quickly, it's net embodied carbon. There is an embodied carbon to the building, even with all these kind of amazing resources that we can still put in the building. At the end of the day, it still takes some carbon for the building to work. A lot of that has to do with the PV, and the PV is being replaced every 20 or 30 years. That turned out to be the largest single item on the carbon impact. If we took the PV out of the actual calculation, then it's essentially net carbon neutral. I'm sure there's things I missed, maybe more concrete, maybe more mechanicals, things like that. But we're getting close to that almost net carbon neutral component. And that's assuming that we can reuse. We're not throwing away the building at the end of its life use. We're reusing the materials in it, like the timber, straw, things like that. And so that's the good news. It's not particularly easy. So part of the idea around zero carbon, net carbon, is the disassembly of buildings as well. So we'll go in and talk with Jay more on what embodied carbon materials means. So Jay, that's my last slide. So it's your
Sounds
your
good.
turn.
I'm ready. If you stop sharing. All right. Well, all's looking good from your end. Excellent. So hello, everyone. My name is Jay Earhart, and I'm a teaching assistant professor at the University of Colorado Boulder, so just down the road from where Andrew is at. And my research and teaching focuses really around embodied carbon, specifically low carbon materials, and also carbon storing materials, as we just got a look at in terms of this Temporal.haus project. And I really look at how the adoption of these materials can be used at scale within building stocks in order to treat buildings as a potential climate solution, leading to drawdown. And so what I'm hoping to share with you today is a bit of a background on what is embodied carbon, why is embodied carbon important in today's built environment, as well as then share with you a framework for how buildings, such as the building that we just saw, can be a part of climate responsive design and a solution to climate change. So buildings release greenhouse gas emissions, and I'll refer to greenhouse gas emissions here as carbon at different stages throughout their lifespan. So if we think about annually between a building constructed today and say 2021 and what that's going to look like going forward, there's going to be an initial pulse of emissions that comes out during construction, or that initial construction, due to the extraction of raw materials from earth, the transportation of those raw materials to the manufacturing site, the energy that's required to turn that raw material, so say iron ore, into steel, and then the transportation from the manufacturing facility to the construction site. And this is what we call the upfront embodied carbon of a building. It's a substantial portion of the total life cycle emissions of a building, or the whole life carbon. And all those emissions happen today during the construction of the building prior to the building even being occupied. Then, as we are occupying the building, we are going to have those space heating, space cooling, and lighting demands, which result in emissions. And the annual scale of these emissions is typically much lower in magnitude than that initial pulse during construction. As we're operating our building, we're also going to have potentially some refurbishment, some retrofit occur at some point in the future. And so that's another aspect of embodied carbon that will get brought in. So sometimes, there's the upfront embodied carbon with that initial construction, but also then additional embodied carbon that comes throughout the course of a project. Additionally, at the end of life, so I haven't shown quite what happens at the end of life with this building. It should be this theoretical building, because it should be lasting well past 2040. But at the end of life, if we're going to be demolishing or deconstructing our building, there will be additional embodied carbon associated with that. So when we couple together embodied carbon and operational carbon, we get what is called whole life carbon. And the whole life carbon is really what we are wanting to reduce over time. The understanding that there's not just the operational carbon associated with the building, but also the embodied is important. And holistically evaluating all these together is needed if we're really going to begin to decarbonize the built environment. So within whole life carbon, about 45 to 50% of the total impact comes from the embodied emissions of a building. For a high performance building, we've done such a good job with passive house buildings, high performance buildings, that much of the distribution of the emissions within a building comes to be about half and half. And we'll come back to this here in just a moment and looking at the cumulative emissions. So understanding the difference now between operational emissions, the heating and cooling of a building, as well as the embodied emissions, think of that as the materials, addressing both those holistically is really important. And so it's important because buildings are contributing today about 39% of global greenhouse gas emissions. So about 40% of all greenhouse gas emissions are coming from the construction as well as the operation of buildings. So if we break this down, about 11% of global emissions are associated with construction materials, and then about 28% from the operations. And the construction materials is really becoming more and more important, because between 2020 and 2050, it's estimated that we're about to build 190 billion square meters of floor space globally. What this equates to is constructing about the equivalent of New York City, in terms of all the floor space that is in New York City, every 29 days. That is the magnitude of how much new construction is going to be demanded across the world. And if we think about half of the emissions for the entire life cycle, for the building to operate for 60, 80, 100 years coming from the materials, those materials are being needed and demanded today. Whereas the operation of that building, that demand is going to be happening decades potentially into the future. And so because of this, about half of all building emissions will be attributed to embodied from the entire global building stock between today and 2050. About half of it will be embodied emissions, and then another half will be operational emissions. So while operational emissions are significant and really important to be reducing, and we've been making great strides across that, attention also needs to be paid to the embodied side of the problem. So to illustrate that, we can think of in a typical building, we're going to have, say, about 75%, and this is, historically about 75%, 80% of the total emissions would be in the operational side. And then a small portion would be the embodied carbon. But as we reduce the operational emissions through more insulative building envelopes, decarbonization of the electrification of buildings and the decarbonization of the electrical grid, that then results in the portion of the operational carbon being reduced yet now the embodied carbon becomes a much larger portion of the pie. So this gets me to the concept of not just building net zero energy buildings, but also looking at what is absolute zero buildings. What is the absolute zero carbon? How can we get not just the operational carbon down to zero and offsetting that with renewable generation, but also looking at the embodied aspect. So if we come back to this, this plot of the annual emissions profile for a theoretical building, we can then plot what the cumulative emissions might be. So from the embodied carbon side, we're going to have that initial pulse. There's not going to be any additional embodied emissions until we maybe retrofit or refurbish our building. But now let's look at what the operational emissions are going to be cumulatively. For a high performance building, these emissions are going to be increasing over time. This will bend down depending upon the rate of the grid decarbonization and how much the building is relying upon electricity. But a high performance building is going to have a break-even point, 15, 25 years after initial construction. If we want to think of an ultra high performance building, this will be one that is not consuming very much energy at all. Well, it's going to have a lower slope. And then if we think of a net zero building, this building is going to have a slope that's nearly equivalent to zero in terms of the carbon emissions associated with it. So as we start moving from typical construction to high performance buildings, ultra high performance from an energy perspective, all the way down to this net zero energy, again, when we add these two together and look at what the whole life carbon might be for a building, a large portion of that is going to be in the embodied emissions. So that's a bit about the separation between operational carbon, embodied carbon, under the whole umbrella of whole life carbon. And coming back to what I started this discussion with is how can buildings be part of the solution, as we inevitably will need to build new buildings for climate refugees, the growing population across the world, as well as the retirement of existing buildings. And so as we start to retrofit and build new buildings, how might buildings become part of the solution and reduce the carbon emissions associated with them? And how we can do that is through the use of carbon storing construction materials. So Andrew just spoke about a couple of those with the timber-based panels, as well as then the straw-based insulation. And those are two types of materials that sequester carbon during the growth of the biomass, as well as then store carbon when they're placed into buildings. So here I'm just plotting the emissions versus the uptake, or the carbon that's sequestered in the material for 1 kilogram of different types of carbon storing materials. And we can use carbon storing materials as both insulation. So examples are blown in cellulose, cork insulation, hemp lime composites or hempcrete, as well as say structural materials. So straw bale construction is a typology of building that we can build residential buildings with, as well as then our engineered lumber, or engineered timber products, and dimensional lumber. You might be surprised in here to see that concrete is a carbon storing material. And that is because concrete does sequester and store a little bit of carbon dioxide through a carbonation process, but know that it's much less than the initial emissions. So it's quite a negligible amount, but concrete does end up storing a little bit of carbon. So now we understand a bit about that there are bio-based materials that store carbon in them, and we can then store carbon in buildings. It's important to understand that when we place carbon into a building, when we place a carbon storing material into a building, it doesn't have we need to measure what its climate benefit is going to be. So just storing carbon and cutting down a tree and placing a tree into a building in the form of wood isn't going to be beneficial until we regrow that tree. So we need to compare the full scope, or we need to look at the full scope of forest dynamics as well as then the climate dynamics. And so what I'm showing here is what the global temperature change will be for 1 kilogram of each of these different bio-based materials. So a positive value on this graph represents net warming. So there's going to be an increase to the global temperature by the use of those materials and due to carbon emissions. And then a negative value represents net cooling, where over time, as we regrow materials, we're going to be sequestering carbon dioxide out of the atmosphere and having a net cooling effect on the climate. And so what we see is for fast growing materials, so for our straw, for hemp, so this brown and light blue line on the bottom here, we see that there is a quick shift initially into net cooling. The use of these materials in storing carbon in construction products and bringing those construction products into a building leads to this net cooling effect. Whereas, and that net cooling effect happens very quickly. In contrast, if we look at our timber-based products, so say sawnwood, which has a rotation period of somewhere around 40 years, as well as somewhere around 75, 90 years, depending upon your forest. And then for your glulam, which has a shorter rotation period of say around 40 years, is what I'm modeling here. We see that this net cooling effect doesn't occur for decades. It takes a long bit of time for that carbon to be reabsorbed by the forest after the regrowth of that tree, before we can count that as a benefit within our building. So what this means is that if we are wanting to look towards meeting 2050 climate goals, and we want to think of buildings as being regenerative and part of the climate solution, it means that we need to start looking at fast-growing crops. So hemp, straw, and bamboo, and incentivize the adoption of these because there is that quick net cooling effect. Whereas for these longer growing crops or forests, so for glulam materials and sawnwood, the impacts are delayed because it takes time to regrow that carbon. So coming back to now putting this all together of what happens when we're going to have some embodied emissions from the initial construction. We're going to need concrete for our foundations of our buildings. We're going to need some steel, as well as emissions associated with just the initial manufacturing. When we couple all this together, we can start to move towards absolute zero carbon buildings, where we are doing well on the energy front with net zero energy. We have those initial embodied emissions, but after the regrowth and we start adopting different bio-based materials, we can start to lead to this net cooling effect where we are offsetting the embodied emissions and really working towards that absolute zero. Yet care must be taken at the end of life. And so while storing carbon in a building is great, it will be released back to the atmosphere if we don't take care to ensure that our construction materials, that are carbon storing construction materials, are reused, are repurposed, and that carbon is locked up in the anthroposphere. We want to keep that carbon in our buildings so that way, and then regrow our trees, and that will lead us to be able to meet near-term climate goals through buildings. And so my key takeaway here is fast-growing bio-based materials are presenting a tremendous opportunity for us to transition buildings to be net cooling, and they will be able to help us meet those near-term climate goals. So thank you for your attention. I'm happy to answer questions in the chat when they come up, but I'll pass it off to the next presenter.
Jessica, you're up. We're going to talk about the energy side.
Yeah, thank you very much, Andrew, and thank you very much, Jay, for that presentation. Happy to pick it up from here. So hello, everybody watching this session. Just give me 1 second to set up my computer. Here we go. Hello, everybody watching this session. So it's great to be here to present alongside Andrew and the other very inspirational speakers on this great project and to share experiences and knowledge. My name is Jessica Grove-Smith, and I'm a scientist.
I want to interrupt you real quick. We're showing your presenter slide, not your.
Oh, I'm sorry. Okay, give me a second. Here we go. Does that work?
There we go. Perfect. Thanks.
Perfect. Thanks a lot, Andrew. Okay, so as I was saying, I'm Jessica Grove-Smith, and I'm a scientist, and I'm also a joint managing director of the Passive House Institute. We're based on the other side of the world. We're based in Germany. And as a research institute, we define and we develop the Passive House standard, which is the standard to which this temporal house was designed.
And my opening quote to this presentation is, what we build today will be our emissions legacy. And that really picks up on what Jay was saying earlier. It encompasses different stages of the building's lifetime. Of course, we need to be looking at the carbon emissions that go into the material choice. What I want to focus on is that aspect of the emissions during the lifetime of the building, during its operations. Buildings have a very long time, very, very long lifetime. And the decisions that we make today in terms of the efficiency level that we design the buildings to, they are decisive for the annual emissions that the buildings will emit during the operation period. So basically, bad decisions today mean that annual emissions from year to year during the operation of such buildings will be high for many years to come. So it's really important and it's really urgent that we rethink and that we build differently. So I'll talk about the importance that high efficiency plays in this transition to build differently and the role that Passive House plays in this. Around 35% of global energy consumption comes from the building sector alone. This picks up also on what Jay was saying. The statistics are fairly well known, and within the UN, within all the climate discussions, it's known and that buildings play an important role and that we need to make a change. And in this whole energy consumption of the building sector, the operational stage is a very large contributor at the moment, because the high efficiency levels, we know how to implement them, but in the existing building stock, they haven't been implemented yet. So we need to make a shift for new builds, and we also need to improve the efficiency levels of the existing building stock. And a large proportion of that is the energy that's being consumed currently for heating and for cooling demand. So the good news is that the technology and the know-how exists to substantially reduce these energy needs during the operation phase of buildings. And basically that's high energy efficiency. And then for an extra step, we can couple that with a renewable energy supply. The Passive House concept, which focuses on high energy efficiency, it was developed for exactly this purpose. It can be applied for new builds. It can also be applied for retrofit projects. It's been around for 25 years and it's being picked up on an international level, which is great to see. It's being picked up by many communities, many municipalities as a pathway, as a solution to meeting the climate goals. And what you see here are just some examples of Passive House projects that have been implemented around the world and that recently were awarded prizes as part of the Passive House Award internationally. So what exactly is a Passive House? We're a little bit limited on time, so I'm not going to dive into the technical details. But as I said, the concept focuses on high energy efficiency. That's what it was designed for. And the general approach is to design buildings under the local context, under the given conditions for high thermal comfort and high indoor air quality. So we have high quality buildings, but they're designed in a way to provide that with the minimum energy input for heating and for cooling. So it's very much a fabric first approach, as Andrew was saying in his introductory presentations, but then also making sure that you have simple and robust heating and cooling system. It's a performance-based standard. So that basically means we've defined a maximum allowed energy demand that you have to design your buildings to. So the buildings are optimized through design and operation to meet these maximum energy targets. And what we're achieving by implementing this approach is energy savings around 90% for heating compared with a conventional building stock. So if you look at these numbers, they're very significant, and those are really decisive for the amount of emissions that you have during the lifetime during the operation of the building. So how the Passive House concept works in details is not part of this talk. The Temporal House is a great example, and there are many, many more examples worldwide. So I encourage you and invite you to take a look at this website, for example, the Passive House database, where you can browse examples internationally. And a special occasion is coming up this next weekend. Every year in November, we have the annual International Passive House Open Days, where residents open their homes and share their experiences. So if you go to this website, have a look, you might be able to visit a Passive House live. And we also have online events where you can learn more from people who have practical experience and who've chosen Passive House as their pathway to move forward as real projects. So in my remaining time today, I don't want to focus only on the energy efficiency aspect, but I also want to talk about the synergies between energy efficiency and the renewable energy supply, because what we need ultimately is both. We need our buildings to be energy efficient, but we need them to be supplied from a carbon-free renewable energy resources to reach our ultimate climate targets, our climate goals. So what I want to highlight in the first place is that high energy efficiency all the way to the passive house is an absolute prerequisite for enabling such a fully renewable energy supply. So this low energy demand that we can achieve by applying the passive house concept is absolutely essential to make a fully renewable infrastructure feasible in the first place. If you're considering aspects such as cost to expand the existing infrastructure to build more renewable energy supplies and the available space that we have in different parts of the world. And it's particularly effective and particularly important to reduce the energy needs in winter. So for the heating demand that we have in buildings, because this is when we typically have a supply gap from the renewable energy sources, which are in many of the parts dominated by solar energy. So these are aspects that we need to take into account when designing our buildings and optimizing them for a renewable energy supply. Now, a concept that is quite popular and well known is net zero as a target for building design. It's very intuitive, yes, it's great, but I'm allowing myself to question it and to suggest an alternative way of thinking about buildings within the context of a renewable energy supply. The problem is that net zero, whilst it's intuitive, yes, you balance out the amount of energy need over the year with renewable energies, it can be fundamentally misleading. So one thing, it's a lot harder for multifamily buildings to reach the net zero target, simply because you have a fairly small roof space in comparison to the living space. And that's a problem. This project, the Temporal.haus that Andrew presented, highlights how important the multi-story buildings, multifamily buildings are from so many social and sustainability reasons. So there's some kind of problem if we discriminate against or if we make it more difficult for multi-story buildings. So we try to look at a different solution. Another aspect that is problematic about simply looking at net zero is that it ignores or it doesn't fully take into account the limitations and the volatility of renewable energy supply. For example, any space constraints or the infrastructure implications that we have when we need seasonal energy storage, transporting or storing energy supplied from solar energy during summer to winter when we actually need it to heat the building. So net zero is useful, but it also has its limitations. So as an alternative, we've developed the so-called Primary Energy Renewable scheme, which was also chosen as a design target for Temporal.haus. And this method was designed to factor in exactly these renewable energy aspects. It specifically calculates how much renewable energy you have to feed into the grid in order to be able to fully cover the energy demand of the building, specifically taking into account any losses that occur along the way. So that is what we generally apply for the passive house standard. And with the PER approach, it's generally essentially a design guideline to optimize buildings for a renewable energy supply. So first of all, we define minimum efficiency requirements as the very baseline. That's our passive house classic standard. That's the prerequisite. Energy efficiency as the starting point as a key. And then for the higher standards, passive house plus and premium, we encourage the use of available space for renewable energy supply, not necessarily aiming for net zero, but making sure that the space that the building is occupied is being used as best as possible, as much as possible for renewable energy supply. This project targeted passive house premium. And as Andrew was saying, that's quite an ambitious target. It meant covering a lot of the roof space, but also making use of the facade for renewable energy supply. And from our studies, from our research, we see that if we apply this consistently, then we can really manage realistically to transition to a fully renewable energy supply for buildings. And with that, I'm coming to a close, and my closing message to all of you today is it's the same message essentially that we'll be bringing loud to the upcoming climate conference at the events that we're attending there over the next weeks. Think efficiency first. Keep in mind how important it is to focus on energy efficiency and reduce the energy needs that we have in the first place. Any energy that we don't need won't imply carbon emissions. So think passive house as an essential ingredient in tackling the climate emergency. Thanks. With that, I hand over to the next speaker.
So thanks, Jessica, for your very interesting speech. My name is Stefan, and I'm in charge of the R&D department of the big fastener group. We are a producer of collated fastening systems, like everybody knows, named staples and nails. Some years ago, it was in 2015, we were thinking about the idea to come over the big steel amount, and find a new solution for connecting timber for construction. And the idea was very small, like every idea was growing. And we showed off the first time at the World Congress of Engineering in Vienna, and showed handmade samples to the very big audience. And we have had a very, very good feedback to continue with this idea. And to begin with, the question is, LignoLoc, what's that? It's a collated nail. It means you can shoot it it's drivable with pneumatic nail guns. It is made out of compressed beech wood. It is for timber and wood-based panels to connect them. All we use is really beech wood. We need a little percentage of glue to hold everything in place after compressing it. And it is a nail with the maximum possible density of wood. I have to check because I cannot see my whole slide. So what are the key features of LignoLoc? What you can see in the picture in the right corner is a driven nail. And this nail produces a kind of temperature. When you drive the nail, you have a temperature in the surface area of about 200 degrees centigrade for a very short while. And this leads to a connection between the nail and the surrounding timber and the surrounding wood. You can see the dark corona around the nail. This is the heat influence zone. And this is something we haven't expected before we started with this invention, but we saw afterwards. And due to this connection, we have a very, very strong bond of this nail in the timber. And we can say that the LignoLoc is the most sustainable fastening system on the market. We can save up to 70% carbon dioxide emissions compared with steel nails with similar shear forces. That means when we are talking about a 3.7 millimeter nail, we don't compare it with the same diameter. We compare it with a nail of 2.5 millimeter because these are nails with the same strength. It is the only fastening system that fully endorses circular economy. That means if you're connecting wood panels or timber to each other, you can cut the connection afterwards, after the period of using the parts. And what you have afterwards is, for example, a panel with a nail inside, and this nail is made out of the same material like the wood around, and you can reuse it again. And this is a very big benefit if you're thinking about circular economy. You don't have to destroy the material and make, for example, panels out of it. You can reuse the material as it is afterwards. We have the lowest thermal conductivity over all fastening systems. This is because of the very good or very bad, however, it depends on how you look like, the thermal conductivity in the wood itself. We have no corrosion, and we have a very high chemical resistance. And we have no tool wear when cutting or grinding the joint wood structure. That means when you make, for example, a CLT panel without glue, only by nailing it together, you can produce everything out of it without damaging any of your tools. And we have a better fire resistance than steel fasteners. This is confusing in the first, but the problem on steel fasteners is that the temperature, if, for example, there's a wall, a surface opposed to a fire inside the room, and the temperature will be guided to the steel fastener inside the substructure, and this leads to a coking, to a coal inside around the nail, and it will the bond will be destroyed before the surface is burned down. This is something we haven't seen on LignoLoc nails. One very big topic for LignoLoc is the so-called LignoLoc cross-laminated timber wall system. We call it LCLT. The name is made by us, is given by us. And this is a wall design that gives every carpenter the ability to build massive timber walls without expensive machinery. Normally, if you're making CLT panels, you need big machines like vacuum presses, or if you go in a very big dimension, like here in Austria, we have a lot of CLT manufacturers. They need a very big room for make these wall elements and very much energy. And the next benefit of this idea is the glue-free diffusion open wall that can be finished with any tool without damaging the knives, as I said before. This, the shown wall design, like you can see on the right side, has an European approval, and the manufacturer is located nearby here from our location, and he is allowed to make these walls for load-bearing usage. He is using approximately 180 nails per square meter, and this wall can withstand in a test 70 tons of horizontal load, which is a lot. Another way of making massive timber walls is nail laminated timber. We call it NLT, and you can also connect the panels with LignoLoc. You can use dowels like it was done in the past, but the benefit of nailing it is a much faster system, and you can save a lot of labor cost. What you need is some kind of sheeting outside to take over the shear forces. Or you can use it as standard. In the US, you call it a 2x4 system. In Europe, it's coded by the Eurocode 5. This system, you can also use the nails to attach the bracing and the diaphragms on the studs. But one thing that is very important for our discussion today is the insulation effect. This test we made in-house here, you can see that we took a 3-layer wood panel, and we fired different fastener to this panel. From left to right, you can see an aluminum screw. This is a typical construction staple. This is the same staple made of stainless steel. You can see here a typical nail, diameter 2.8 millimeter and 50 millimeter long. The same nail made from stainless steel. And here you can see the 3 different LignoLoc nails with the different diameters. And here with the thermal camera, you can see the light. The more you can see, the more is the thermal transport of heat. And we did the test with a refrigerator. Inside the fridge was minus 23 degree, and outside in the room we have had 27 degree. That means the difference between inside and outside was 50 degrees centigrade, means 19 degrees Fahrenheit. And we go to the next page. We measured the outside temperature on the nails, like in the side we can look from the room at. And you can see minus 23, like I said before, and 27 outside. And on the aluminum nails, we have 10.3 degree. On the staples, 12.6 degree. On the stainless staple, 73 degree, and so on. And you can see that the biggest effect was on the LignoLoc nails. We have a thermal conductivity of 0.64 watt per meter Kelvin. And you compare it with stainless steel and standard steel, you can say that we are 90 times lower than standard steel and 22 times lower than stainless steel. That is standard. That is used for connecting wood fiber insulation, for example, here in Austria and in Germany. You can also see one very big benefit, the condensate on the nails. It means we have it here in our test visible, but normally you have this condensation inside the wood, and it means that this moisture can cause a lot of rot and mold inside the wood, inside the timber. These pictures are taken out of was taken out of a publication from Dane Christensen in 2010. And you here can see the thermal impact of steel fastener inside the construction. And this is something where we think this is the biggest benefit for LignoLoc, besides all the other benefit. If you want to avoid the thermal transport of heat from the inside to the outside or the other way around. Thank you for your attention. Yes, it's a short presentation, but LignoLoc is only a short thing of the whole system. And I only wanted to introduce you what we can do and what's about LignoLoc.
Okay, I think it's my turn now. Thank you for having me. I'm going to present the Ecococon wall system. My name is Björn Kjerulf. I'm the CEO of Ecococon, and I'm happy to contribute to this roundtable. I hope the whole slide is visible. Our system is a modular system. It's a Lego-like construction for rapid assembly. It consists of 6 different types of panels that can be produced at more or less any size, and it's always individually adapted to the specific building we are creating. So we can really design in advance, more or less with millimeter precision, the exact geometry of the house, and that makes, of course, everything very quick to build on the building site. So this modular system is a great feature. But why do we use straw, you would ask, in insulating? It's like not the usual material that is being used for insulating a building. Now, it does have a lot of advantages. First, it's a natural carbon sink. I'll talk a little bit more about that later, as you will see. And it's rapidly renewable. So it takes 1 year for straw to mature. It takes 50 years for a tree. And it's also abundantly available. I'll get back to that. Maybe one of the things you have discovered last year is that when wood prices soar, even what we thought was kind of a normal material to use in the building site becomes kind of unavailable. That's when you start to understand that maybe using straw really is an advantage because of the abundance and because it saves the amount of wood you would use in the construction, where you can maybe use the wood more strictly for load-bearing construction. And the straw has a very good thermal insulation value. It also has a long phase shift time, so it takes time for any heat to show up on the inside. It has a very good protective values in summertime, and it has a great fire rating. All of these I will get into a little bit more in detail. So straw has a lot of advantages. Let's look at one of the first one. It's the abundance. In Europe alone, you have 144 million tons of straw being produced on the fields every year. It is, they say that about a third of this amount can be used in a sustainable way for other things. The rest should be returned to the ground to achieve some carbon restorage of the ground itself. And then if we take, so that would be 48 million tons per year. If we then use just 10% of that sustainably harvested straw for, let's say, our walls, we end up with 100 million square meters of straw walls that could potentially be built annually. This is just mind-blowing in my opinion. It creates million tons of CO2 that are stored in this material. And as you saw from the presentation by Jay, this is really what has an impact, like in the first few years. Now, the second thing people are always asking about, well, straw burns. Yes, it does, but thanks to the compression of the straw, there is it more or less smolders on the surface. I have here a video. I hope that will come true. As you can see, it's the wood that burns, and the straw, which is in between the studs, is not really where you see the flames coming out. And to the left, you can see after we tested a wall segment, 3 by 3 meters, and after 39 minutes, the test was stopped. We tested it directly with like 1,000 degrees going directly onto the straw. And as you can see, if you dig a little bit into the charred surface, just a few centimeters under the surface, you will find this golden straw sticking out. So it's quite amazing, how well this keeps up. And so we reached array 30 without any surface coating at all, just by using compressed straw, which I think is just fabulous. Of course, we do use surfaces. The normal buildup is again done with sustainable materials. Let's look at the inside first. We apply directly on the straw. In fact, that's one of the main advantages of Ecococon, is that we can put clay plaster directly onto the straw surface. We don't have any OSB board or anything else in between. It goes directly onto the straw surface. There is a mesh in it, and the fine clay plaster can cover it. Today you can have all kinds of colored clay, beautiful interior surfaces created with clay. And these layers protect the straw in an amazing way. In fact, again, we reached 120 minutes of fire protection with a 3 centimeter clay layer on the straw surface itself. So that means that we are able to build really demanding constructions with such a value. On the outside, we have developed maybe a counterintuitive solution, at least for most architects who know that the airtight layer should always be on the inside, and please keep it that way. But in our case, you can really put it on the outside, because we are using an airtight but diffusion open membrane with an SD value that needs to be lower than 0.2 meters. It's WUFI tested. It is tested in practice, even in climates like Finland, and it works brilliantly. It has an extra advantage that while we are building with our straw, we wrap it the same day and are able to protect it against weather influences during construction. So this thin membrane, which is not that sustainable, it's a polyethylene or polypropylene membrane usually, does have a huge advantage in the way how it's built, like a practical advantage. And we cover this membrane with the wood fiber board, or we have been using now also a straw fiber board, which then can be directly plastered with the render, or it is possible to have a ventilated facade. So, thanks to this build-up, we are able to create a very well insulated construction without any thermal bridges, because the wood is also separate. I'm hearing some feedback here. No? Is it okay? Good. So, of course, the first thing we did was we got it certified by the Passive House Institute as a passive house component. We think this is important to set the right standard from the beginning. It is also certified cradle-to-cradle product, and I think it's the only cradle-to-cradle or passive house component that is also cradle-to-cradle certified. So these two combinations, I think, is where the future needs to be. So, as a case study, I just want to show this one building in the Netherlands. It's a gym, and it was built thanks to the Venlo municipality that asked for a cradle-to-cradle certified materials. And we were able to provide them with it. Of course, it was designed with some metal construction because that's the cheapest way, but still, thanks to the modularity of our panels, we were able to kind of fit whatever need there was on the building site, which is kind of one of the advantages here. So, of course, that enabled us to sequester quite a few tons of CO2 in this building. So a little bit about us. We originated in Lithuania. I'm definitely not the designer behind this. I've come up with some ideas, but I'm quite happy that we have been able to implement these buildings now in Slovakia, where I'm based, close to 50 buildings now in the last 10 years. And the production volume is growing, the interest is growing, and our goal is, in fact, to have some local production in each market. So, although it is a more centralized production at the moment, of course, that wouldn't be a very cradle-to-cradle approach. So the idea is to set up rather smaller production units all around in Europe and hopefully in other places of the world as well. So for this, very much thank you for your attention. If you want to know a little bit more, just go on our website, ecococon.eu. And just remember, it's easy to build with renewable materials today. Thanks a lot.
Thank you, Raquel.
Thank you.
We have some questions.
Yes, there are actually a couple of questions coming from the public. And we can start with a comment actually for you, Andrew, from Robert Youngberg. He said, always enjoy your presentation. My son and family live near you. Evacuated from the forest fires last year and 3 times 8 years ago. The climate disaster way too close to home. So this is a really powerful comment. Thank you, Robert, to be present at this panel today and to leave your comments on YouTube.
Yeah, you know what I can say is that I've gotten a lot of controversy now, especially around timber and kind of the quality, as Jay alluded to, the 50-year grow back period. There's a lot of controversy about new forest or plantations versus old growth, things like that. The idea of embodied carbon is like ridiculously complex, and it has to do with I'll show examples. Like there are forests that were planted as carbon sequestering forests for carbon credits. Some of those forests burned in California this year, for instance. I live about maybe about half the forest in the county where I live near Rocky Mountain National Park, is now burned. So what we think about in terms of biomass and usable biomass and carbon cycles is completely disrupted in the real world compared to some of our scenarios that we create. So it's a very dynamic process. And, I think the first thing is to use less and use it wisely. And that's kind of why I thought that using the CLT panels as a structural earthquake resistant material, but transferring back to the straw as much as we could, using those best practices where they're best used in our built environments, case by case, building by building, is a good metric to work by, rather than maybe getting too involved in kind of the politics or kind of the complexity of the carbon question itself. Like that should not keep us from moving forward, because it's a very dynamic situation. I think you in Venice know that better than almost anybody in the world right now with the water.
In Venice, yes, it's a really complicated situation, and of course also dive into politics and all these bureaucratic aspects is not helping. It's just delaying the problem, and there's no time for further delays here. So
I think when we first spoke is when you had that historic flood, right?
Exactly. Yeah. Exactly, which was a disaster. You can find images online. It was really something that shocking, really shocking. You could swim in Summer Square. The water was above my head. It was really shocking. Yeah, I invite everyone also from the public to search on Google for to discover the situation after the flooding after November 12th, 2019. Was really, really shocking, yes. So first question from the public for Andrew. Hi to everyone, I'm George Sullivan. Has the project been modeled to the UNFCCC ISO 14,000 family of standards to report to the Equator Principles and report to the UNFCCC Climate Neutral now? Okay,
I'm just a guy who's working up in a small passive house in Colorado. So my scope of developing that level of detail is not there yet. But I should say that the Passive House Ribbon, the pH Ribbon plugin calculator, is based on the RIBA's carbon standard use cycles, and also there's a whole host of material libraries that they see, and a lot of it's based on what Jay went over. The assumption of reuse of materials, or being back into the atmosphere again, or materials being replaced periodically. And I find, at least in America, I found firms already, large firms, not using that level of standards. So I'm hoping that the RIBA does track the UN, and that we have a common language on assumptions for carbon within the buildings.
Thank you. And same person, George, asked, did you use EPDs? Renewable energy has a carbon footprint. Solar and wind is 8 to 15 grams per kilowatt hour. And what grid efficiency number did you use? The US is 2.8.
Yeah, actually, that's a really good question for Jessica, and that goes directly around the primary energy renewable process. I don't know, Jessica, if you want to chime in on what we use for grid assumptions.
Yeah, I can chime in. It's going to be a bit difficult to keep it short because this is a whole nother can of worms, so to speak. So with the conventional approach, where we look at kind of the primary energy impact of the grid, the conversion factor, it depends on the country. In the US, it's 2.8, but it comes a little bit back to what I was mentioning, why I alluded to in my presentation, is that I think we need a switch from current design systems where we look at just source energy factors to the whole shift of how do we actually rate buildings, how can we optimize buildings in the context of renewable energy supply. So looking only at these conversion factors as they currently exist, which basically look at what is the fossil fuel footprint of the building, won't work anymore as the energy supply transitions from fossil fuels to renewable energy. We need a whole different way of thinking, of rating kind of the energy supply of buildings, and that's what we're trying to address with the scheme of the renewable primary energy. So a shift basically from the current grid conversion factors, which only look at fossil fuels and rate renewable energies at absolutely clean and no problem, and we can ultimately use them endlessly, to a new scheme where we say, hang on, how much renewable energies do we actually, what is the impact of this building on a renewable energy supply? That's the shift that we're doing with the renewable primary energy scheme, and that's also how this project has been assessed. So basically looking at how much renewable energy do we have to provide to be able to cover the energy needs of this project.
And Jessica, can I ask a quick, sorry, Bjorn, I was going to ask how does energy storage work in that, now that that's become such a popular topic? Is that also in the PER?
Yes, so that factors into the PER in terms of that we compare over the course of the year, we can compare the dynamics between when is renewable energy available and when is it actually needed at the building. And we basically run a simulation over the course of the year, and we see what is the mismatch between the two and how much storage do we need in between. And any storage is associated with losses. If it's just over a course of a day or maybe a week, then we can work with batteries, and the technology is increasing or improving continuously. So the efficiency of those short-term storage systems are quite okay. That's not a problem. The problem or the impact, the significant impact happens when we're talking about seasonal storage. Renewable energy supply, we often have a lot more in summer because we just have a lot more solar energy during summer. But the peak energy demand of buildings in many parts of the world is the heating season. So there's a complete seasonal mismatch there, and any renewable energy storage that we have to store between summer, or from one season summer to another season winter, has significant losses. So on an order of magnitude of maybe 70% losses. So we're only going to actually get 30% of that produced energy to the building itself, and that's taken into account in the renewable primary energy scheme.
Well, I wanted just to address, I think, a little bit the elephant in the room, and which is it seems like this building is a great example of how it should be, but it's kind of, as if you look at the other buildings that are being built, nobody's really doing it this way, and all possibilities are there. We can calculate PHPP, like Passive House is on the market for 30 years now, and we have renewable materials we can build with, and still it doesn't kind of move forward as we would like. The understanding of the public is kind of detached. Even the professional public is detached from I think what we know, like as we are sitting around this table here. So how to address this, I think, is the big question. How to get that over to the layman. So that's something I would like to hear some ideas about. Yeah.
That's the big question, and that's what we're all working on, I guess. That's why we're here. I think like showing these kind of projects is real, having impact, showing people that there are solutions, that it can be done. I always think the one project that's built and that you talk about and talk about and talk about and present it to others, encourage them to follow suit, is really helpful. And I do see, or my impression at least, is that a lot of policymakers are now becoming aware what role buildings actually play in the overall scheme of things of emissions, and they're really looking for solutions in the building sector. the policy can be really, really slow to catch up, because it then gets to the point where you have to redefine, you have to tighten targets, you have to see how does it fit into the whole political scheme and the policy scheme and the funding scheme. And those processes are really slow. So if we can find a way to remove the barriers and say quicken that uptake of the solutions that already exist, is it whether it's passive house or the low embodied carbon materials, any mechanisms that we have to remove barriers, if there's a way in policy to recognize solutions that already exist and incentivize those solutions, I think that could speed up the process. I don't know what anybody else's thoughts on that are, but removing barriers, I think, is a really important part. And then knowledge transfer, training, especially the younger generation, making sure that we don't continue in the same steps, but we actually have a transition and the next generation builds differently.
Thank you, Jessica. I think you are now also providing an answer to Brown Wineberry, who said, thanks so much for this excellent presentation. Question for presenters: what policy do these presenters think would accelerate adoption of more buildings like Temporal.haus, Ecococon, LignoLoc, passive house? So I think you both, Jessica and Bjorn, sort of answered these questions. I don't know if anyone else from the speakers wants to add more to this.
I would probably start with the codes. You know, if you can adapt the codes so that it makes it easier. There are lots of codes out there that makes it more difficult if it's fire regulations or other codes. And I think the other thing is that it needs to be calculated the correct way. You know, that I think Passive House Institute has been talking about that for many years, that return on investment isn't calculated the right way, and banks haven't understood it. So there are kind of limits there as well, which should be easy from a logical point of view, easy to kind of remove these barriers, because an investment in energy efficiency usually pays back over the time. Yeah.
There was a question coming from the public during Jay's talk. You should include refrigerants, water, trash, recycling, occupant travel. This was for Jay.
Sounds good. My internet's a little bit spotty, so if I cut out, let me know. But when we're calculating body carbon, a systems thinking approach is required. The transportation is certainly important, and it depends upon where you draw your system boundary around what are you including and what are you not including. And so there are some standards and some standard ways of accounting for that, and that all gets rolled up into what are called the life cycle inventories that then you are using to calculate the embodied carbon of your building. So refrigerants is a big one that's being addressed right now from the mechanical heating, ventilation, and cooling side. So that's coming in there. But yes, all of these other components get worked into those life cycle inventories.
Okay, thank you. And another question also for you, Jay, from Ivan Aiden. Timber reduces carbon, but we cannot say it is carbon neutral if we consider how it gets to site. Is treated prior to install, and does the consumer add back the trees that are taken out of the ground?
Certainly, and this goes along the same lines as to when I was talking about timber as being a sustainable material, that requires the replanting. And so a forward-looking approach where when we take a tree and put it into a building, we can't consider it to have a climate benefit until that carbon is regrown in the tree. And when you do the math around it, timber and the carbon content of timber is about 0.5 kilogram of carbon per kilogram of material. The cradle to gate emissions of the manufacturing of the transportation are actually quite low in comparison to the amount of carbon that can be stored. So it can actually be or timber, and incentivizing the use of timber from sustainably managed forests that are neutral around their own boundaries, and the push of harvested wood products from those forests into buildings does have a net cooling effect on the climate due to the amount of carbon that's then stored in buildings. But again, the caveat there is you need to ensure that the carbon is stored for long periods of time within those buildings, because at the end of life, if you just burn that timber, well, then your carbon emissions just go right back out. And that goes for timber, straw, really any bio-based material.
Although I can just add to that, as you have an annual crop like straw, we saw it from your presentation, it's an advantage because the effect is fairly immediate. Although at the end of life, it is a big question. But again, I hope in 60 years' time, we will have solved this problem of overheating and of the globe. Otherwise, we are not in a good position anyway. So hopefully, we can recycle some of it or find some ways to mitigate that as well.
Thank you, Björn. Would you like to add something more to the conversation? Do you have questions for each other? Or I don't know, Andrew, if you would like to wrap up the presentation of today.
I just, I want to thank everybody very much for coming. And I think, Bjorn, to your comment is like, I think the policy thing is something kind of outside of my scope, but I do know that when we bring in the people who are inventors, the manufacturers, the designers, the engineers, the kind of people who touch with the public, like the European Cultural Center, when we create these kind of synergies and opportunities, policy follows that. I think that's kind of the way I envision it, especially with the work that Jay does, especially on the macro side. When buildings are big for individuals or for humans, but when we look on the policy side, we are having lots of conversations around food and transportation, and it's a solar versus materials, urban versus rural. It gets really complicated quickly for the policy people. But I think when we show that we have these processes that do multiple things well at the same time, and they bound beyond what our typical understanding, especially in the built environment, is concerned, then policy can quickly adapt to that. I often think about like the electrification of transportation is stunning, how it's changing people's concepts just in the past couple of years about how they will buy their next car, for instance. And I would like us to have that conversation about how they'll build their next building within that same kind of framework or same kind of intensity. And I believe we offer something more because we're offering something that will last for many generations, not just maybe a dozen years or so. So that's kind of my 2 cents on that concept. So if anybody wants to add to that or I'd love to hear more thoughts.
No. Well, all right. It was a pleasure for ECC to host this really interesting, informative, stimulating conversation. And I invite all of you to visit the presentation by Andrew at Palazzo Mora. For those who cannot visit in person, of course, we made the presentations available online through the virtual tours. And stay tuned for more interesting conversation with the participant of our architecture biennial. And if you have questions, I'm sure you can reach out to the speakers directly and they will be happy to get back to you with the information you need. Thank you very much, all of you, and hope to see you soon in Venice or somewhere else in the world. Grazie. Thank you.
Thank you.
Bye-bye.
So much.
Bye.
Bye.